Today, I will give you a brief overview of my work under the title Well-Posedness and Exponential Stability of your shulman thermoelastic system with porous damping and distributed delay time. My work is as follows: introduction, second preliminary, well-posedness, then exponential stability, and some references. According to the thermoelasticity theory, a body's deformation is connected to change in enthalpy and consequently a change in temperature. In other words, thermoelasticity is the study of the relationship between the material thermal conductivity and the pressure as well as elasticity and temperature. In the classical model of heat diffusion, heat flow is governed by Fourier law of thermal conductivity, which is considered as the best foundational equation for modeling heat conductor, and states that the heat flow is proportional to temperature gradient. However, this model has a major drawback, as it uses physical inconsistency for the infinite speed of heat diffusion. In other words, any thermal disturbance at one point will instantly transfer to other parts of the body. As a result, many researchers were interested in developing a new constructive relation to resolve this paradox, such as the theory of Lord Shulman, which is based on the study of the system of four hyperbolic equations with heat dissipation. In this case, the heat equation is also hyperbolic as opposite of the parabolic one obtained from Fourier's law. In this work, we are interested in studying the following one-dimensional Lord Shulman thermoelastic system with porous damping and distributed delay time acting on the porous equation represented by 1. With the initial data and the new delivery boundary conditions, where ρ1 is the mass density, G is the product of the mass density by the equilibrated inertia, 2 is the relaxation parameter, which is assumed to be small but strictly positive. The coefficient beta 0, beta 1, 0, delta is 0 are positive constant, denote respectively the coupling between displacement and temperature, the coupling between the displacement and the volume fraction, the coupling between the displacement and the porosity, the thermal conductivity and the thermal capacity. The constitutive parameters define the characteristic of the material satisfying inequality 2. And mu1 defined by where lambda and mu are the usual damping parameter. The variable u, Barphy, and theta are respectively the displacement of the solid elastic material, the volume fraction, and the temperature. The initial data belong to Swift function space, and the term defined by is the distributed delay time. Only which is acting only on the porous equation, and gamma 2 is the boundary function, where 2 are two real numbers satisfied. In this section, we introduce some transformation and say that the assumption needed in our work. We introduce the following new dependent variable represented by 3, which is satisfies 4. Consequently, the problem 1 is equivalent to 5, with the following initial and boundary condition. And the weight of the data, we assume that 7 is holds. And if we set the new variable, we can get that the moyenne of the new variable is equal to 0. Thus, quantary inequality can be applied on new variable. In addition, simple substitution shows that U bar for theta is the solution of problem 5 with the initial data for U bar given us. In what follows, we work with U bar, but for convenience, we write U instead of U bar. In this section, we give the existence and uniqueness result for problem 5-6 using the semi-group theory. We introduce the new vector function U and the new dependent variable V and C. And we define the energy space by H and the two space H1 equal and equal. And for any U, you type in H, we keep H with the inner product defined by. Then the system 5-6 can be written as follows, where A is a linear operator defined by and the domain of I is given by where the space H equal is defined by. Then for any U from DA, we have the inner product on H equal to, which is inferior or equal to 0. From where it follows that the operator A dissipative. Now, by using the last unigram lemma and classical regularity argument, we can prove that the operator is surjective. Hence, A is maximal dissipative, and therefore the A is dense in H. So, by using Lorentz-Phillips theorem, we deduce that A is an infinitesimal generator of linear C0 semigroup on H. And we have the following well-posedness results, which is the existence and uniqueness theorem. We move now for the exponential stability. In this section, we use the energy method to prove that system 5-6 is exponential stable. To achieve our goal, we need the following lemma. And we start by the energy functional defined by which is satisfied the estimate. To define the Lyapunov functional, we need the following lemmas. We have 5 functions. We start by the function P1 has defined by and satisfies the estimator. Function E2 defined by and satisfies for any epsilon 1 positive thrmoelastic the estimator. For each radial defined as and satisfies for any epsilon 2 positive. E4 defined by and satisfies the estimator. And finally, E5 defined by and satisfies the estimate. Now we define the Lyapunov functional by where n and ne are positive real numbers. We choose the next. The Lyapunov functional satisfies the equation 9, which means the equivalent between the energy functional and the Lyapunov functional, and satisfies. We move now for stability theorem. We have if let U for theta z be the solution of 5-6 and assume that 7 holds. 7 is the assumption of the white delay. Then the solution decays exponentially. That means that there exist 2 positive constants from the one and the 2 such that to prove our theorem, we're using the equivalence between the energy functional and the Lyapunov functional. We did use 11. and the simple integration of 11 curve we get them, which gives us the serial results and by using the other side of 9 again to prove its complete. And finally, some references. And thank you for your attention.